Proxima Centauri, the closest star to our solar system, has long captivated astronomers. Discovered in 1915 by Scottish astronomer Robert Innes, this dim, diminutive red dwarf is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its relatively short distance of approximately 4.24 light-years from Earth, Proxima Centauri remains invisible to the naked eye due to its faint luminosity. Yet, its scientific importance is profound, particularly as the host of Proxima B, an exoplanet located within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and live far longer than stars like our Sun. Their lower brightness means their habitable zones lie much closer to the star. For Proxima Centauri, this translates to a tight orbital distance of just 0.05 astronomical units, a fraction of the Earth-Sun distance. However, this close proximity exposes Proxima B to intense stellar activity, including frequent solar flares and high levels of radiation, conditions that could drastically affect its atmosphere and surface, making it quite different from Earth. The discovery of Proxima B marked a major breakthrough in exoplanet research. Using the radial velocity method, astronomers detected tiny wobbles in Proxima Centauri's motion caused by the gravitational pull of an orbiting planet. These subtle shifts allowed scientists to estimate the planet's mass and orbit. In 2016, the European Southern Observatory confirmed the planet's existence, a landmark moment in the search for potentially habitable worlds beyond our solar system. Despite these insights, ground-based observations face considerable challenges. Earth's atmosphere distorts incoming light and limits the ability to gather detailed data about Proxima B's surface and atmospheric composition. As a result, much of what we know, including the planet's size, distance from the star, and orbital pattern, is derived from indirect methods. To truly understand Proxima B's environment and its potential for life, we need more advanced tools, such as the James Webb Space Telescope, JWST. JWST represents a revolutionary leap in astronomy. Designed as a successor to the Hubble Space Telescope, it was specifically created to overcome Hubble's limitations, especially in observing the infrared spectrum. While Hubble mainly captures visible and ultraviolet light, JWST is optimized for infrared observation, enabling it to see through cosmic dust clouds and reveal phenomena that remain hidden to other telescopes. One of JWST's most significant innovations is its 6.5-meter wide primary mirror, more than twice the diameter of Hubble's. Coated in gold to maximize infrared reflectivity, this mirror is composed of 18 hexagonal segments that operate in harmony to collect faint, distant signals from across the universe. Another key feature is its 5-layer sun shield, which keeps the telescope's instruments at a frigid minus 233 degrees Celsius. This extreme cold is essential to prevent the telescope's own heat from interfering with its sensitive infrared sensors. Unlike Hubble, which orbits Earth, JWST is stationed at the second Lagrange point, L2, a gravitationally stable spot about 1.5 million kilometers from our planet. This remote location minimizes thermal and optical interference from Earth, allowing JWST to operate continuously and with unmatched precision. As the closest stellar neighbor, Proxima Centauri serves as a gateway to understanding exoplanetary systems. Proxima B, in particular, remains an intriguing candidate, an Earth-sized rocky planet that may harbor water and, under the right conditions, even life. But the challenges posed by its harsh environment make it a complex puzzle for scientists to decode. With instruments like JWST, we now stand at the threshold of a new era, one that could finally reveal whether life exists beyond our solar system. The James Webb Space Telescope, JWST, is equipped to explore everything from the universe's earliest galaxies to the atmospheres of distant exoplanets, like Proxima B. Its advanced ability to detect infrared light is especially crucial, as it allows scientists to observe redshifted phenomena, objects whose light has been stretched to longer wavelengths by the universe's ongoing expansion. But JWST's capabilities go far beyond observation. It's a revolutionary tool designed to tackle some of science's biggest questions, including how galaxies formed, how stars are born, and what conditions might make other planets suitable for life. Outfitted with cutting-edge instruments like the near-infrared camera and IR-cam, the mid-infrared instrument MIRI, and the near-infrared spectrograph and IRSpec, JWST serves not just as a telescope, but as a cosmic time machine, a laboratory in space, and a tribute to human innovation. Among its many targets, Proxima B has emerged as one of the most intriguing. Located just over 4 light-years away and orbiting within the habitable zone of Proxima Centauri, this Earth-sized planet has captured the imagination of scientists and the public alike. With a mass roughly 1.17 times that of Earth, Proxima B is likely a rocky planet, and its proximity makes it an ideal candidate in the search for extraterrestrial life. However, Proxima B is no Earth twin. One of its most notable characteristics is tidal locking. One hemisphere always faces a star in perpetual daylight, while the other remains in eternal night. This creates extreme temperature contrasts across the planet. Yet the terminator line, the narrow band where day transitions to night, may offer moderate conditions, potentially capable of sustaining liquid water and possibly life. Still, life on Proxima B would face enormous challenges. Its host star, Proxima Centauri, is a volatile red dwarf known for intense solar flares, violent bursts of X-rays, and ultraviolet radiation. These energetic events could slowly erode the planet's atmosphere and expose the surface to harmful space weather. To retain an atmosphere under such conditions, Proxima B would likely need a strong magnetic field as a protective barrier. Without it, the surface environment could be extremely inhospitable to known life forms. Even so, the potential for life cannot be ruled out. Proxima B's position in the habitable zone hints that liquid water might exist, perhaps not on the surface, but beneath it in more stable subterranean environments. Scientists draw parallels to Earth's extremophiles, organisms that thrive in extreme conditions, such as deep-sea vents or high radiation zones. If life exists on Proxima B, it might employ similar survival strategies, resisting radiation, inhabiting underground shelters, or developing alternative biochemistries. Exploring Proxima B is more than a scientific endeavor. It's an existential journey aimed at answering one of humanity's oldest and deepest questions. Are we alone in the universe? This nearby exoplanet, residing in the habitable zone of our closest stellar neighbor, represents one of our best chances to find out. Yet, any hope of habitability must be tempered by the reality of Proxima Centauri itself. Unlike our Sun, this red dwarf is smaller, dimmer, and far more active, which brings its habitable zone extremely close, just 5 cents compared to Earth's $1 Australian. As a result, Proxima B orbits very near its star and is constantly exposed to intense flare activity. These flares unleash powerful streams of high-energy particles that could strip away an atmosphere over time. Even if the planet retains some atmosphere, the constant ultraviolet bombardment may hinder the formation of complex organic molecules, making it difficult for life to emerge or persist. Nevertheless, Earth provides examples of resilience in the face of extreme environments. Organisms that thrive in high-radiation environments, such as Deinococcus radiodurans, often called the toughest bacterium on Earth, have evolved the ability to repair extreme DNA damage. If life exists on Proxima B, it may have developed similar or even more advanced adaptations. The planet's tidal locking could offer a natural form of protection. Its permanently dark side might shield potential life from harmful radiation, while subsurface habitats like caves or underground oceans could provide further refuge. This makes Proxima B a compelling target for astrobiology. Studying its environment could redefine what we consider habitable, pushing the boundaries far beyond Earth-like conditions. Its relative proximity to Earth allows for continued observation through powerful instruments like the James Webb Space Telescope JWST, as well as future observatories currently in development. While the question of Proxima B's habitability and whether life actually exists there remains unanswered, its discovery has already expanded our understanding of where and how life might arise in the universe. It stands as one of many intriguing exoplanets in a rapidly growing catalog of potentially life-supporting worlds. JWST plays a key role in deepening this understanding. Its spectrometers can detect and analyze chemical signatures in exoplanetary atmospheres, such as water vapor, methane, and carbon dioxide, that may indicate biological activity. Identifying these markers is crucial to assessing a planet's ability to support life and uncovering signs that life might already exist. Although Proxima B draws much attention due to its location and conditions, it's not alone. Other promising exoplanets orbiting sun-like stars, some discovered by NASA's Transiting Exoplanet Survey satellite TESS, are also excellent candidates for future exploration. As more planets are found within their stars' habitable zones, the possibility that life is widespread in the universe becomes increasingly plausible. These discoveries highlight a larger scientific challenge: understanding the complex interplay of factors that make a planet truly habitable, including atmospheric chemistry, stellar activity, geological dynamics, and more. As space technology evolves, so does our ability to directly examine the climates and surfaces of distant worlds. Future missions may follow the path of Mars rover programs or target the icy moons of Jupiter and Saturn, offering insight into how life might survive in drastically different environments. These efforts will also shape how we investigate Earth-like exoplanets, including Proxima B. Ultimately, the search for life beyond Earth is about more than just discovering other organisms. It's about redefining our place in the cosmos. While Proxima B may not be a second Earth, it reminds us that potentially habitable environments can exist far from our own. The drive to explore continues to demand scientific innovation and bold exploration. In the coming decades, we're likely to witness discoveries that profoundly change our view of life and the universe. Whether we detect microbial life on Proxima B or find a truly Earth-like planet orbiting a distant star, every step brings us closer to answering one of humanity's oldest and most important questions. Are we alone? What was once the realm of science fiction is now one of science's most thrilling frontiers.